Cryptographic random numbers. Explanation with Dephi source explaining how to generate random numbers with proper sources of entropy and hash functions. Cryptographic random numbers / source code Bellow simply calling randomize and using the random procedure is a severe security flaw in applications seeking to protect data with random numbers. A random number generator gets its randomness from entropy. Borlands Random procedure uses a 32-bit seed as entropy, and that seed is generated by the randomize procedure, which gets its entropy, the system time and date, which are very probabilistic and can be tested for quickly. To generate random numbers that cannot be differentiated from pure chaos is a very difficult task on a computer, mainly because you rely on internal states that are often too predictable. The idea is to gather entropy from the least predictable states of the system and dilute that entropy inside a much larger pool. The pool I refer to is the internal state of the random number generator. What it is: there are important properties that have to be respected when generating random numbers. More specifically, random numbers intended for encryption. The properties that implicated in this random number generator's design are strongly based on Bruce Schneier's Yarrow, www.counterpane.com. The first property is to ensure there is always enough entropy in the pool before outputting random numbers so that the pool never enters a weakened state where the next random numbers that are output have predictable information. The next property comes in handy if you're going to be using the generator to make session keys that will change multiple times during a chat session. It is important that one compromised key will not reveal any of the previous keys nor any of the next keys that will be used. To do this, we need to eliminate the mathematical relationship between the random numbers that are output and the state of the pool. The third desired property implies that even if the entropy gathered from your sources is of poor quality, fairly predictable, the pool must not suffer for the low entropy and the output random numbers must not show any evidence of this. I have tested this unit extensively. The final and most crucial test centered around the third property. To make an extreme case, I started the pool with nothing but zeros in it and generated 12 megabytes, 100 million bits. I used the die-hard battery of tests, http://stat.fsu.edu/geo/diehard.html, and it passed all 15 with flying colors, without collecting any entropy. With this I am satisfied of the random number generator's performance and submit it to you to use as a secure alternative to what is commonly seen in programs. How it works: Two entropy gatherers are created. One, a thread that tracks mouse movement at random intervals, taking 4 bits of entropy from the mouse position and state of the system's high-resolution timer. 2, a latency calculator that gets 4 bits of entropy from the high-resolution timer when called by the main app. This is used by alling tKeyGenerator.add latency on the onKeyDown event of an edit box, to count hard drive latency, or IRQ latency, when either of the entropy gatherers has accumulated 32 bits. It sends it to the entropy pool. The entropy pool takes in entropy 32 bits at a time and uses it to fill an entropy buffer of 256 bits. When the buffer is full, a primary reseed is executed. The primary reseed updates the primary pool, a hash context, internal state of a hash function, with the entropy and XORs it with the pool's seed. This seed is used similarly the way Randomize generates RandSeed. After every primary reseed, the seed, with now 256 bits of entropy, is ready to be used to output random numbers if the calling application so desires it, but it will continue to reseed and gather entropy regardless of that. After 8 primary reseeds have taken place, a secondary reseed is executed. The secondary reseed updates the secondary pool with the contents of the primary pool and then flushes the contents of the primary pool into a state with no entropy. The secondary pool is persistent in that it is never flushed and will carry entropy bits from various reseeds. A completely new seed is generated from the secondary reseed, whereas the primary modifies it with entropy. This secondary reseed prevents backtracking properties, guessing previous states of the pool, and ensures there is entropy in the pool even under conditions where new entropy is of poor quality. When the calling application needs to generate a key, it calls safeGetKey, which ensures that no more than 8 sets of 256 bits of random numbers can be generated from a single reseed. To do this, a key reserve counter is incremented every primary reseed, and cannot exceed 8. When you generate a set of random numbers, the key reserve is decremented and the function will return fastly if the key reserve is at 0. Note: an application can ignore the key reserve and call forceGetKey. This is very risky practice and I seriously discourage you from using this function. The random output created by getKey is generated with the entropy pool seed. The seed is used as an encryption key and then permitted, with an expansion compression. The new seed is used as data to be encrypted. It is encrypted with the previous seed and expanded compressed in 64 rounds. These rounds ensure that it is impossible to determine the state of the seed, the primary pool, the secondary pool or the entropy buffer, in turn, preventing anyone from finding the previous or next outputs. Notes: assign a variable of type T key generator and call its .create. This will start the process. When you are done, call .destropy. You can use .keyCount to find out the state of the key reserve, how many getKey calls can be made before the next reseed. I strongly condone raising the value of max_key_reserve. You can manipulate the speed at which entropy is gathered from the mouse by setting the mouse_interval constant, in milliseconds. A value lower than 10 is unrecommended. No error checking is done to ensure there is a high-frequency counter on the system. This should be verified by the calling application. If there is no such counter, the random number generator will work but will output non-random numbers. The application must provide 32 bytes of memory space in a variable to pass to the getKey functions. No error checking is done here. You may change key_build_rounds to any value greater than or equal to 32, but larger than 64 is quite useless. Important note: the source Bellow is part of a library in progress cumulating 3 years of my research. If you want to use it in a program, a little bit of credit would be nice. nscript.pa contains a pseudo-random number generator that comes from an unknown source, and these implementations of Havel and Rayondale are severe modifications of David Barton's Havel.pa and Rayondale.pa found in the DCP-CRYPT 1.3 component suite. Download nscript.txt and rename it nscript.pa. Silly webost. I've included the cryptographic functions separately because they total 1,300 lines together. http://www.ekientrix.com/computer/drmonkey/nscript.txt. The actual website is www.drmonkey.com. // You'll have to deal with the documentation above. Unit Noise Sponge interface uses Windows classes controls nscript const seed_size equals 8 primary _reseed equals seed_size secondary _reseed equals seed_size / parameters max_key_reserve equals 8 key_build_rounds equals 64 mouse_interval equals 10 type key 256 equals array 0 seed_size 1 of long word T noise sponge add entropy equals procedure, block long word, of object. T noise sponge procedure equals procedure of object. T mouse collector equals class. T thread protected PCTXPRNG underscore CTX XY integer block long word bits gathered long word interval frequency this time last time T large integer send mouse entropy T noise sponge add entropy public constructor create procedure sync send mouse entropy procedure execute override and T latency collector equals class protected block long word bits gathered long word time T large integer send latency entropy T noise sponge add entropy public constructor create procedure measure latency and T entropy pool equals class protected seed key 256 entropy buffer key 256 primary pool Havel underscore CTX secondary pool Havel underscore CTX primary seed count byte entropy count byte key reserve byte procedure permit essayed procedure primary seed procedure secondary seed procedure adentroe block long word public constructor create and T key generator equals class protected entropy pool T entropy pool mouse collector T mouse collector latency collector T latency collector public add latency T noise sponge procedure constructor create destructor destroy override function key count byte function safe get key var key boolean procedure forced get key var key and implementation constructor T mouse collector dot create begin inherited create true randomize prng init at pctx ran seed free on terminate equals true priority equals tp normal resume and procedure T mouse collector dot sync send mouse entropy begin send mouse entropy block and procedure T mouse collector dot execute var nil handle pointer idled boolean begin nil handle equals nil bits gathered equals 0 idled equals false query performance frequency repeat if idled equals false then begin message wait for multiple objects 0 nil handle false mouse underscore interval 0 idled equals true and query performance counter this time if this time last time interval then begin if x mouse dot cursorpus dot x and y mouse dot cursorpus dot y then begin x equals mouse dot cursorpus dot x y equals mouse dot cursorpus dot y inc block, x and 15, x or, y and 15, x or, this time and 15, SHL bits gathered, inc. Bits gathered 4. If bits gathered equals 32, then begin PRNG init. At PCTX block, synchronize, sync send mouse entropy, block equals 0. Bits gathered equals 0, and interval equals PRNG at PCTX mod mouse underscore interval div2 plus mouse underscore interval asterisk frequency div1000 query performance counter last time idled equals false and else begin query performance counter last time idled equals false and until terminated equals true, and constructor tLatency collector dot create begin inherited create block equals 0, bits gathered equals 0, and procedure tLatency collector dot measure latency begin query performance counter time inc block time and 15 SHL bits gathered inc bits gathered 4. If bits gathered equals 32, then begin send latency entropy block equals 0, bits gathered equals 0, and constructor tEntropy pool dot create begin inherited create havelinit at primary pool havelinit at secondary pool filchar seed size of seed 0 entropy count equals 0 primary seed count equals 0 key reserve equals 0 and procedure tEntropy pool dot permit said var temp buffer array 01 of key 256 PCTX PRNG underscore CTX HCTX havel underscore CTX I byte begin for I equals 0 to seed underscore size 1 do begin PRNG init at PCTX seed I temp buffer 0 I colon equals PRNG at PCTX temp buffer 1 I colon equals PRNG at PCTX and havelinit at HCTX havel update at HCTX temp buffer size of temp buffer havel output at HCTX seed and procedure tEntropy pool dot primary seed var temp seed key 256 I byte begin havel update at primary pool entropy buffer size of entropy buffer if primary seed count begin havel output at primary pool temp seed For I equals 0 to seed underscore size 1 do seed I colon equals seed I x or temp seed I, inc. primary seed count, and else secondary seed. Filchar, entropy buffer size of, entropy buffer, 0. If key reserve entropy count equals 0, and procedure T entropy pool dot secondary seed, begin have output, at primary pool seed, have update, at secondary pool seed size of, seed, have output, at secondary pool seed, permit essayed, have init, at primary pool, primary seed count equals 0, and procedure T entropy pool dot add entropy, block long word, begin move, block pointer, long word, at entropy buffer, plus, entropy count asterisk size of, block, caret size of, block, inc. Entropy count 1, if entropy count equals primary underscore reseed then primary reseed, and constructor T key generator dot create, begin inherited create, entropy pool equals T entropy pool dot create, mouse collector equals T mouse collector dot create, mouse collector dot send mouse entropy equals entropy pool dot add entropy, latency collector equals T latency collector dot create, latency collector dot send latency entropy equals entropy pool dot add entropy, add latency equals latency collector dot measure latency, and destructor T key generator dot destroy, begin mouse collector dot terminate, latency collector dot destroy, entropy pool dot destroy, inherited destroy, and function T key generator dot key count byte, begin result equals entropy pool dot key reserve, and function T key generator dot safe get key, var key boolean, var temp seed key 256, temp buffer array 01 of key 256, rctx radiandale underscore ctx, pctx prng underscore ctx, hctx havel underscore ctx, ij byte, begin if entropy pool dot key reserve equals 0 then begin exit, result equals false, and else result equals true, move, entropy pool dot seed temp seed size of, temp seed, entropy pool dot permit essayed, radiandale init, at rctx entropy pool dot seed, for I equals 0 to key underscore build underscore rounds 1 do begin radiandale encrypt, at rctx temp seed 0, radiandale encrypt, at rctx temp seed 4, for j equals 0 to seed underscore size 1 do begin prng init, at pctx temp seed j, temp buffer 0j colon equals prng, at pctx, temp buffer 1j colon equals prng, at pctx, and havelinit, at hctx, havelupdate, at hctx temp buffer size of, temp buffer, havaloutput, at hctx temp seed, and move, temp seed key size of, temp seed, dec, entropy pool key reserve 1, and procedure t key generator forced get key, var key, var temp seed key 256, temp buffer, array 01 of key 256, rctx rayundale underscore ctx, pctx prng underscore ctx, hctx havel underscore ctx, ijbyte, begin move, entropy pool seed temp seed size of, temp seed, entropy pool permit essayed, rayundale at rctx entropy pool seed, for I equals 0 to key underscore build underscore rounds 1 do begin rayundale encrypt, at rctx temp seed 0, rayundale encrypt, at rctx temp seed 4, for j equals 0 to seed underscore size 1 do begin prng init, at pctx temp seed j, temp buffer 0j colon equals prng, at pctx, temp buffer 1j colon equals prng, at pctx, and havelinit, at hctx, havelupdate, at hctx, temp buffer size of, temp buffer, havaloutput, at hctx temp seed, and move, temp seed key size of, temp seed, if entropy pool key reserve end, c, copyright drmonkey, 2001, www.drmonkey.com, drmonkey@hotmail.com